All right, welcome back, Physical Science 20. Here's the last few examples. Hopefully we can run through them in this video. Sun Young places a 2 kg block of aluminum that has been heated to 100 degrees C into 1.5 kg of ethyl alcohol that has an initial temperature of 18. What is the final temperature? So that's the key thing with these. Trying to figure out what is it you're asked to find out. So sometimes it's C, sometimes it's M, sometimes it's going to be a T. So that's the key thing you have to look for. So let's see, we have aluminum, then we have alcohol. All right, so aluminum, always call it metal again, it doesn't matter. 2 kgs, hey, it's already in kilograms, so we don't have to do anything. We don't have to do an initial calculation. The CM, the specific heat value of aluminum, we looked at that in another video, 9.2 times 10 to the 2. And initially it was at 100. Then it's placed in ethyl alcohol, and we don't know what the final temperature is. That is what we are going to be figuring out. So we'll just leave the expression like that. Alcohol, let's see, it's in the liquid form here, so let's call it that. 1.5 kgs, hey, it's already in the form that we need. The specific heat capacity of the liquid here, alcohol, 2.46 times 10 to the 3. 2.46 times 10 to the 3. And it was initially at 18. Final temperature, we don't know. So again, it's going to look like that. And the setup is very similar to the previous example. So if the thermal energy released by the aluminum, there we go. The energy released by the aluminum is equal to the energy gained by the ethyl alcohol. So it gives us a net change of 0. So M metal, C metal, delta T metal, plus, oh, I did it again. So again, use some magic here. This should be M liquid, C liquid, delta T liquid equals 0. Okay, so the aluminum is 2. Specific heat capacity, 9.2 times 10 to the 2. Temperature change, TF minus 100. So yes, not the greatest, but that's the best we can do. 1.5. 2.46 times 10 to the 3. And then the last part I'll squeeze in right here, TF minus 18 equals 0. So again, can multiply that term, those two terms, multiply these two terms. When I do this, I get 1,840. And then over here, 1.5 times 2.46 times 10 to the 3, 3690. Okay, and then yes, distribute. So 1840 multiplied by TF, 1840 multiplied by 100, that's 184,000. 3690, then 3690 multiplied by negative 18, and then common terms, right? I have my TF terms, and I have my other terms here that don't have a variable in them. So 1840 TF plus 3690 TF gives me 5,530 TF. Then negative 184,000 and negative 66,420 gives me negative 250,420. And then to get the TF term by itself, Add this. And then lastly, yeah, hey, if you can do this question, you can do them all, because it's the trickiest manipulation if there is one. Where are we at here? 5530. There we go. So TF works out to be 45.283 degrees C, which is, let's run it off to 2 sig figs, 45 degrees C. All right, let's look at the next one here, the last one. A metal bar is placed, it's 4 kgs placed into boiling water until its temperature is 100. The bar is then placed in water. They reach the same temperature. What is the specific heat capacity of the metal bar? So we have the metal, and we have water. So the M metal, we're told, is 4 kgs. It's in kg, so we can leave it like that. We don't know this, so it's a mystery. We don't know what the metal is. That's what we're asked to find out. And maybe its identity is on our list, maybe it's not. So initially it was at 100. So you have to read the question. You have to imagine it always like this. You have a piece of metal. Okay, we're heating it up. It has a TI. And then you have water that has a TI value. And that you're going to place into there. Okay? So they have different initial temperatures. And then after a while, they reach the same temperature. So this is what you have to envision for all of them. They have different initial, and usually the metal is being heated up. So it's heated up, placed in water or alcohol, whatever it is, which is that. Usually it's close to room temperature. And then what happens? What's the final temperature? So imagine all these questions like this. So initially the metal was heated up to 100 degrees C. Then it was placed in water until they all reached 35 degrees C. So if I fill in my little diagram here, we have that. TF minus TI, 35 minus 100. So that gives us negative 65.0 degrees C. And the water, it is 500 mils. So MW, 500 mils, but of course, water's density is 1 gram is 1 milliliter, or vice versa. So 500 mils is the same thing as 500 Gs. And of course, that has to be in kilograms, so move the decimal 3 places to the left. Specific heat capacity of water. Of course, we've looked that one up already. We have that. Be careful, if we're talking about ice ever, ice, of course, is a different value than liquid water. 2.1 times 10 to the 3. All right, so TI, water was initially at 20, but then we put that hot metal in, and it reached the final temperature of 35. So if I'm going along over here, the water was initially at 20. So you can see the schematic there. Hot metal, room temperature water, bring them together, they reach that temperature. So delta T is TF minus TI. 35 minus 20, 15. All right, so now we can set it up over here. Q metal plus Q water gives a net change of 0. So everything for the metal, everything with the water, then hopefully we'll have enough room here to squeeze everything in. 4.0 cm. So that's what we're looking for. Negative 65. And then water. And then what do we have here? We have 15. Ooh, just barely squeeze it in. Okay. Over here, it's all multiplied, but I'll multiply the numbers here. 4 times negative 65 is negative 260. And then over here, if I multiply all of these numbers here, 0.5 times 4.18 times 10 to the 3 times 15, 31,350. Okay, again, I want to get this term by itself, which means subtracting this from each side, because it's plus, so it's minus. You can see everything's going to work out nicely here, because I'm going to have a negative on the left and a negative on the right. When I divide, it's going to work out to be a positive, which is what it needs to be, because specific heat capacity is positive. 120.5769 joules per kilogram degrees C. If I round that off to 2 sig figs, I'll put in scientific notation too. So the decimal goes after the first non-zero digit. It's going to be 1.2. Let's see, that's a 5, so that bumps up to 1. And then 2 places to the right. So 1.2 times 10 to the 2 joules per kilogram degree C. I don't think there's one like that on the list. I guess it's close to lead, so we could say lead. But in the question, I didn't ask for the identity anyway. All right, we'll stop there. We have one little piece to do, and then that'll be it for this section.